Hello, everyone. Welcome to another session of this Gamma seminar. It is my pleasure to introduce our speaker today, Bartosz Zawora from the University of Warsaw, who will talk about reduction of K-contact structures. So, Bartosz, the floor is yours.
Thank you very much. At the beginning, I would like to say that the results I will present during this talk are obtained in collaboration with Javier De Lucas, Xavier Rivas, and Silvia Villarino. So the structure of the talk is the following. At the beginning, I will introduce some basic notions from K-symplectic geometry. And then I will move to some modified K-symplectic reduction theorem, Marsden-Weinstein reduction theorem. And then I will say how this K-symplectic can be translated to K-contact and conversely. And then I will introduce basic notions of K-contact geometry and proceed to K-contact Marsden-Weinstein reduction. And at the end, I would like to show you some examples if time permits. Okay, so at the beginning, let me introduce the definition of K-symplectic manifolds. So first, we define a K-symplectic form on a manifold P, and this form is, first of all, RK value form, differential two forms, sorry. It's closed and non-degenerate, then the pair P omega. I would like to highlight that all RK valued things will be denoted as bold in bold notation. Okay, so the pair is a K-symplectic manifold, and in our setting, in the K-contact setting, it will be important to, we will deal with K-symplectic, but when omega is exact, namely that bold omega is the differential of some RK valued one form theta. And then P theta is an exact K-symplectic manifold. So let me recall that the non-degeneracy, first of all, the RK valued differential two form can be seen as a collection of K two forms, differential two forms that are closed. And the non-degeneracy condition can be translated as the intersection of the kernels is equals 0 everywhere. Okay, and in the reduction procedure, we will need K-symplectic orthogonal. Is somehow analog, generalization of just symplectic orthogonal, which we retrieve in the case when K equals 1. So we define, for a subspace WP, at some point K-symplectic orthogonal, we'll denote it as this, and these are all vector fields such that the bold omega on WPVP is equal to 0 for all vectors in a WP. Okay. So let me introduce the one homogeneous K-symplectic manifolds, because as we'll see later, the K-contact manifolds will somehow correspond to a particular case of one homogeneous K-symplectic manifold. So first of all, R cross just reals without 0, and 5 is a principal Lie group action on P. And then K-symplectic manifold P omega is one homogeneous K-symplectic manifold if we have this for every element S in the group R cross. This is the multiplicative group. And note that and one homogeneous K-symplectic manifold is exact because we can write from Cartan's magic formula, we can write that the omega, that this condition can be written as is this, right? So we get that omega is the differential of some theta, where theta is defined here. Okay, sorry, I didn't define this vector. It's the Liouville vector field. So in other words, the fundamental vector fields with respect to the action phi, sorry, which is dilations. I mean the action that acts for dilations. Okay. So later on later on in the K context, in the contact setting, sorry, the theta will be defined as the contraction of omega bold with this Liouville vector field. Okay, since we want to perform a reduction, we have to have symmetries, and so we define a Lie group action is an exact K-symplectic Lie group action relative to an exact K-symplectic manifold if the action lives invariant the tautological form. So it can be written as a Lie derivative of bold theta with respect to the fundamental vector field is equal to 0, where xip denotes the fundamental vector fields, which are the vector fields that are tangent to the orbits of our Lie group action, basically. Here is the definition. Okay. So now we define the K-symplectic momentum map associated with an exact K-symplectic manifold. So we have Lie group action, and we define the momentum map as a contraction of fundamental vector fields with the tautological form, and it's equal the pairing of the of this momentum map with element xi, and of course here the momentum map, this K-symplectic momentum map, can be seen as a collection of maps from P to G star. So this means that this contraction, I mean, it's G phi alpha xi xi. Sorry, it's tensor E alpha. All right. So keep this in mind that this arcade, yeah, this can be seen as the collection of map J phi with an index alpha. Okay, it's this definition of this K-symplectic momentum map differs when we differs with the standard one, since the standard one is defined as a contraction. Standard definition is the contraction fundamental vector field, sorry, on P with bold omega, and this is D J phi paired with xi. But when our Lie group action is exact K-symplectic Lie group action, we can retrieve the standard momentum map. Okay. The K-symplectic momentum map here, I mean, in general, whenever it's standard or exact, is an equivariant if this condition holds for every element in G, when the G with index K is a tensor product of standard adjoint actions. It's the standard definition, and in other words, you can express this definition as via this diagram, saying that it is commutative for every G in a Lie group, for every element of a Lie group. So in standard k-symplectic manifolds, when we deal with k-symplectic Lie group actions, of course, not every momentum map is ad equivariant. However, it can be the whole procedure. I mean, the Marsden-Weinstein reduction for k polysymplectic manifolds can be generalized to not ad equivariant momentum map, because we always make it. I mean, the momentum map, we always make it equivariant with respect to different action on G star. Okay, so it doesn't matter, but since we deal with an exact k symplectic momentum maps, these momentum maps are always ad k equivariant. So we restrict ourselves to ad equivariant momentum maps. Okay. So now we have a very general k-symplectic reduction by a submanifold, which says that if S is a submanifold of P, and we have injective immersion. So let me draw a picture. You probably all know this picture, but let me draw it anyway. So here we have k-symplectic manifold. Here we have some submanifold S. We also assume that the kernel of omega pulled back to this S has constant rank. And then it defines a foliation Fs on a manifold S, which gives a foliation. And we also assume that there is the canonical projection S to S divided by this foliation is a submersion. And we get that, so let me draw. Here we have some foliation induced by the distribution given by kernel omega pulled back to S, and then we can reduce. I mean, we have this pi. We reduce. Yeah, we reduce to S divided by this foliation, and this is k-symplectic manifold, reduced k-symplectic form. And one can also show that this kernel is given by TPS tangent space to S intersected with its k-symplectic orthogonal. So now in standard k-symplectic Marsden-Weinstein theorem, we want to take TPS. I mean, we want to take S equals J phi to -1 of mu, and get that kernel J omega bolted P is equal TPS J phi to -1 of mu intersected with TP J phi to -1 of mu K orthogonal, and we want that this is equal TP G mu G mu P. We want it because in general it doesn't hold. But this would somehow retrieve if this equation, if this equality is true, this would somehow retrieve the Marsden-Weinstein scheme for k-symplectic manifolds. Yeah, and actually it was done by Silvia Villarino and Juan Carlos Marrero and others in the paper of reduction of k-symplectic manifolds, I believe. And they give conditions to ensure that this equality holds. But in our case, it's not sufficient when we want to perform the k-contact reduction, which means that we will deal with one homogeneous k-symplectic manifolds. It's not sufficient to take as an S, J, the level set of mu. Of course, here is bold mu everywhere. Sorry for that. In our case, we will want to take as an S J phi to -1 of R cross K mu, and later on you will see why. Okay, so basically we want to modify the classical Marsden-Weinstein k-symplectic reduction to deal with subsets, the submanifolds given by J phi to -1. Sorry, I will denote K here. Where R cross it's reals without 0, and R cross K mu is an invariant set with respect to dilations in each component of mu alpha. Okay, so basically we define this as a point in P such that there exists an element in lambda 1, lambda K as an element in R cross K, such that J phi alpha, which is the alpha component of the k-symplectic momentum map, is equal lambda alpha mu alpha, and it's for every alpha. So you see that this submanifold, I will talk about the conditions to ensure that this is indeed a submanifold, but you see that for sure it's something bigger than we have this -1 of mu bold. So it's something bigger. So you may ask, what about the quotient group? And you may ask if it's remained the same or not. And of course, the answer is not, because in the k equal 1, it's easy to see that dimensions of reduced manifold do not agree, in the sense that the reduced manifold in the k-symplectic sense, when k equal 1 we get symplectic, you may obtain a reduced manifold that is odd dimensional, which cannot be symplectic. So yeah, of course the quotient group will change, and let me show you how. So we fix mu as an element in G star. Okay, now we are talking in not about the arcade value elements. Of G star. We just take G star, we take an element mu of G star, and we define K mu as the intersection of kernel mu with respect to the natural pairing. It's written here. And we define G mu with brackets as an element of the algebra, such that their adjoint action, dual one, for that at star psi of mu wedged with mu is equal 0, which can be equivalently written as psi in elements of the algebra, such that at psi mu equals kappa mu for some kappa in R. Okay, and you can see that particular case, when kappa is equal 0, you get the standard Lie algebra of the isotropy group of a point mu in a dual Lie algebra. This proposition says, we consider something general, and this proposition says that this K mu is a Lie subalgebra of G. Since it is a Lie algebra of G, there exists a simply connected group K mu such that this Lie algebra integrates to this subgroup K mu. It will be sorry. Yeah, we have G. Sorry, K mu in G, and then on the levels of subgroups we have this. Okay, so yeah, let P omega be a K-symplectic manifold. Let a bolded mu be an element of G star K, which is G star, I mean K copies of G star. Be a weakly regular K value. I will say in a moment what is a weakly regular K value of K-symplectic momentum map, but for now you only need that this condition ensures that the J phi to -1 R cross K mu is a submanifold of P. We have a Lie group action. We define K mu. I mean, it can be proved that this K mu bold is the intersection of all subgroups K mu with indices alpha, and the same with at the level of Lie algebras. And we have that we have the following conclusion, that the tangent space of K mu P is the subset of the kernel. Is the subset of the kernel J star mu omega P. So now you see that in general we don't have this equality, but in the Marsden-Weinstein reduction procedure, we would like to find conditions. I mean, yeah, we would like to find conditions under which this equality holds. So in general, when we have space given by J mu omega P, right? So in general, we have that it's not, I mean, the whole space given by this is not generated by the tangent space to the orbit of the subgroup K mu P. So we have something like this. Okay. So now let me discuss conditions that guarantee that J phi R cross K mu is a submanifold. So it's enough to say that that we'll deal with a weak regular value mu of a K-symplectic momentum maps, and this will guarantee, if mu is regular value, then J phi, the general J phi to -1 R cross mu is a submanifold of P. But we need something more. I mean, we need that every J phi to -1 alpha R, sorry, this here is K, R cross mu alpha is a submanifold of P. So to ensure this, we will assume that each mu alpha is a weak regular value of J phi alpha. And then if every component of bold mu is a weak regular value of J phi alpha, then of course the bolded mu is weak regular value, and we will call it that bolded mu. When this holds, the bolded mu is is a weak regular K value of the momentum map J phi. But of course, I mean, converse doesn't hold. When mu bolded is a weak regular value, it doesn't mean that each of the component is a weak regular value of J phi alpha. And maybe let me simply recall, shortly recall quickly that what the weak regular value is. So when we have map from M to N, then X in N is a weak regular value of F if the counter image of X is the tangent space. I mean, for some M is equal the kernel of the MF, and if the counter image of X is a submanifold of M. Okay, so let me show you a simple example when we deal with non-regular, weak regular value. So consider a map R cross to R such that it takes XY and maps to X squared. Okay, so and call it F. So then if R2, then you can see that the tangent space X 0 YF0 is d over dy, since this is this space. So of course, I mean, here we have so tangent vectors are d over dy. Okay, but if you compute the contraction d over dx with dx squared, you get that this is x, and restricted to this counter image f to -1 of 0, you get f(0), you get that this is 0, but d over dx, of course, does not belong to this tangent space. So 0 in this case is not weak regular value nor regular value. Okay, so let me move further. Okay, so to perform a k-symplectic reduction, a modified k-symplectic reduction, we need some analog of the standard reduction lemma, which says in the like classical symplectic setting, you know that we have something like this, that the tangent space to orbit generated by G mu is the intersection of the tangent space to the orbit generated by the whole G, intersected with the level set of the momentum map. And the tangent space G to -1 of R, sorry, not R, mu, is the k-symplectic orthogonal, sorry, not k, I mean k equal 1, which is symplectic orthogonal of this omega. So this is the classical reduction lemma you all probably know. So we need some analog, some modification of this lemma, and indeed we have one. So let P omega be an k-symplectic, an exact k-symplectic manifold. So now restrict to k equal 1. Exact symplectic manifold. G mu is a group, it's a subgroup of G such that add star g to minus 1 of mu wedge with mu is equal to 0. So similarly, we can translate it as a condition that this is proportional to mu. Yeah, it's proportional to mu. We assume that mu is a weak regular. Sorry, it shouldn't be k. Value of a symplectic momentum map associated with a symplectic Lie group action, and then we have the tangent space. So let me draw a picture again. P, let me say theta. So this is our exact symplectic manifold. Here we take the level, it's not the level set, but here we have the j phi to minus 1 of r cross mu, for mu being weak regular value. So this is indeed a submanifold of P. Here we have the space generated by the action of a Lie group, so it's just an orbit GP, and we have the intersection of this tangent space is the tangent space first to j phi to minus 1 of r cross mu intersected with the tangent space to the orbit is g mu with brackets. I mean, it's the tangent space generated, tangent space to the orbit generated by this subgroup j mu, which is, of course, something bigger in general than the tangent space to the orbit generated by g mu in general. Okay, and similarly, we have that the j phi to minus 1 of r cross mu is a symplectic orthogonal of the tangent space to the orbit generated by the whole group intersected with the kernel of the tautological form theta at P. And since P omega, I mean, is symplectic manifold, we have that double symplectic orthogonal gives the same space. So we can also write that TP, the tangent space to minus 1 of r cross mu, symplectic orthogonal gives this. Okay. So now you can now you can state the reduction, the theorem, Marsden-Weinstein reduction theorem for contact manifolds when k equal 1, because you have this. Yeah, because you have this, that double symplectic orthogonal gives the same subspace. So in general, I mean, we have that j r cross mu divided by tp j phi to minus 1 of r cross mu intersected with tp j phi to minus 1 of r cross mu symplectic orthogonal. We know from previous general reduction theorem for k-symplectic manifolds, if k equal 1, but we know that this is the kernel of of j mu, sorry, mu omega. This is equal this. So now using this lemma, it's very easy to show that I mean, this is applying this lemma, we get that J phi to -1 of R cross mu is the intersection, I mean, the phi to -1 of R cross mu intersected with the GP kernel theta P, right? And this is the PG phi to -1 of R cross mu divided by the group K mu P. And we get a result that this is one homogeneous symplectic manifold. I mean, in this case, vector space. But yeah, J phi to -1 R cross mu divided by K mu is the one homogeneous symplectic manifold. And we will use this lemma to prove the K contact Marsden-Weinstein reduction. But here we have a generalization of standard reduction lemma from just symplectic setting. In K contact setting, it's more difficult because we don't have that double K symplectic orthogonal is equal the same space. We don't have it, so in general, we cannot repeat what we did a second ago. So we will need some conditions, technical conditions that will ensure that this kernel of K I mean the RK valued two forms is equal the tangent space to the orbit generated by some subgroup of G. Okay, and the proof to show this consists two steps. First step is to show that V alpha vector space defined as this V alpha defined as this is an exact symplectic vector space, where projection P alpha is a projection from TPP to TPP without the kernel of omega alpha. We just remove the kernel of omega alpha at P. Okay, so I mean it's very easy to see that this, of course, is a symplectic vector space because we remove the whole kernel of omega alpha. So omega alpha by definition is closed, and on this space is non-degenerate. And we also will denote in the square brackets psi p of P in square brackets, just the projection of psi on the fundamental vector fields on P to this vector space without the kernel of omega alpha at P. So this is the first step. And the second step is to show that K-linear surreactive morphism from this space, which is our candidate for the reduced K symplectic manifold, this morphism satisfies that their kernel, the intersection of the kernel is equal 0, and they are surreactive. So these are the two steps that will allow us to prove that this equality holds. Okay, but this is very technical. So what's the main idea behind this proof? So basically, the result will follow from this lemma. So we start with some collection of symplectic vector space V alpha omega alpha. And now if we find, I mean, for P alpha, and P alpha is a projection from V to V alpha. And now it's easy to see that if this condition holds and P alpha are reactions, then we have that omega bold, V omega bold with omega bold defined as P alpha omega alpha. Right, sorry about the indices. Is k-symplectic manifolds. So this is the main idea that stays behind the proof. So now we construct V alpha. We will construct V alpha defined as like on the previous slide, is this. We show that we find conditions for this P alpha P morphism to be first of all surjectives, and that the intersection of the kernels is equal to zero. And then we use this lemma, so we get that this V alpha, which in our case will be this space, will be k-symplectic manifold. So that's the main idea. Okay. So roughly, I mean, just roughly speaking, we can say that we prove Marsden-Weinstein reduction theorem for k-symplectic manifolds, and also later on, as you will see, for k-contact manifolds. In the case when we can retrieve this k-symplectic structure or k-contact structure from other symplectic and contact manifolds, when we can we can pull back this k-symplectic structure from symplectic manifolds. So this is the idea, because in general, I mean, it's very difficult to find conditions when this curve J mu omega bold is equal in standard case this. Okay, but as you will see never mind. So this is the main idea, and indeed we have a proposition that ensures that V alpha is a k-symplectic is an exact symplectic vector space. So this is the first proposition, which proves the first step of the Marsden-Weinstein modified Marsden-Weinstein k-symplectic theorem, and the second step is that the so V alpha is a symplectic an exact symplectic vector space, and now we want to find conditions for linear maps P alpha P to ensure that they are surreactions, and of course P alpha is a surreaction if and only if this condition holds. And similarly, we can find a condition that ensures that the intersection of the kernels P alpha is equal to 0 if and only if this condition holds. I mean, these results are very technical, but basically they ensure in our case, since we take J phi to -1 of R cross mu, these conditions ensure that a kernel J mu omega is given by K mu P. So if we have this equality, we can state that the modified k-symplectic Marsden-Weinstein reduction theorem, which has this form, but shortly we start with one homogeneous K-symplectic manifolds, we assume that mu is a weak regular K value to ensure that J phi 2 minus 1 R cross mu is a submanifold of P. We have a Lie group, K-symplectic Lie group action, an exact, K-symplectic Lie group action that acts free, and actually it's quotientable manner on J phi 2 minus 1 of cross mu to ensure that the reduced space is indeed a manifold. And as I said before, we assume these two conditions to get that the reduced space defined as here is a one homogeneous K-symplectic manifold, and the K-symplectic structure on the reduced manifold is related to the initial one via this relation. Okay, so we have modified K-symplectic Marsden-Weinstein reduction, but only for an exact K-symplectic manifolds. It doesn't have to be one homogeneous, but exactness is enough. Okay, so now you may ask, how is it connected to K contact setting, and let me explain it in a moment. So let me recall that per M eta is a K contact manifold, where eta is a where this bolded eta belongs to is a one form arcade value, one form on M, such that the kernel of the bolded eta is a regular distribution of corank K, and kernel of D bolded eta is a regular distribution of rank K, such that the intersection gives 0. So we can write that Tm is the kernel of bolded omega plus the kernel of the eta. Okay. Of course, here we consider only the so-called coorientable contact manifolds, which means that we have locally, we have globally defined K1 forms that satisfy this condition in the definition of K contact manifold. There exists more general approach, but I recommend to read a recent paper titled "Foundations of K contact manifolds," written by Javier De Lucas, Xavi Rivas, and Tomasz Sobczak. Okay, so for a K contact manifold, we have a unique family of rep vector fields, and they satisfy that the contraction eta beta with the rep vector field R alpha is the delta alpha beta, and the contraction the rep vector field R alpha with d eta equals 0. They commute between themselves, and in addition, they give rise to a basis of the rep distribution given by the kernel of d eta. Okay. And again, since we want to perform a reduction, we need to have symmetries. So a Lie group action on M is a K contact Lie group action if it leaves invariant K contact form for every element in G. In other words, for compact Lie group, we can write the derivative of the bolded eta with respect to the fundamental vector field is equal 0 for every element in G. And now you may ask, okay, but what about if K equal 1? We can consider the symmetries that do not leave the invariant contact form, but they give something proportional. They give something like f eta for non-vanishing positive definite function, and f And of course you may write, but this is a separate case. And also this approach to contact reduction with such Lie group actions also can be generalized in our language and in our approach. But let us stick to the k-contact Lie group action that leaves invariant a k-contact form. Okay, so yeah, I was talking for more than half an hour about k-symplectic manifolds. So how are they related to the k-contact manifolds? And the following theorem gives us the answer. So let eta be a one-form arcade valued differential one-form on M. We have the projection from R cross times M to M. And S denotes the natural coordinate on R cross, where let me recall that R cross is just reals without zero. And then the theorem states that M bolded eta is a k-contact manifold if and only if R cross times M with omega with omega defined as the derivation of S times the projection of bolded eta, pullback of the of bolded eta with respect to this projection, is a k-symplectic manifolds with some vector fields R tildes are with tildes on R cross M such that the intersection, the contraction omega beta with R tilde alpha is equals minus tilde alpha beta ds. The minus comes from that we have S first. And the contraction ds with R tilde alpha equals 0 for every alpha and beta from 1 to k. So now the question is how to retrieve the k-contact structure from k-symplectic structure from the reduced k-symplectic structure on p mu omega mu. Well, let me recall that this is j phi to minus 1 R cross mu k mu. Okay. Yeah, I can. It's okay. I just only tell you that these conditions, that the existence of this R tilde vector fields are it's very important, because otherwise you may get that you can simply show that for omega bold as defined as ds projection eta defined as where eta 1 is equal to projection, let me equal dx1 plus x3 dx4, and here eta 2 is equal dx2 plus x2 dx1. Okay, so you can easily show that the kernel, the kernel of omega is equal 0 on maybe I should, it's on R cross times R4. And this is of course k-symplectic, but on M, which is R4 with eta 1, eta 2, it is not k-contact, since the kernel of d eta is equal 0. Okay, so we really need this condition that there exists the k vector fields R1 tilde to Rk tilde satisfying these conditions. Okay. So for a k-contact manifold, we define a k-contact momentum map associated with a Lie group action in such a way that oh no, I'm sorry, it's wrong. it's not how we define it. I'm so sorry. We define it as the contraction omega with bolded eta is j phi eta paired with psi. This is the definition of a key contact momentum map. Okay. So now we can retrieve we can move from K contact setting, we can move to K symplectic setting. So we consider this manifold, and this is K symplectic manifold. We can for this manifold we can define the extended momentum map, which it gives that the momentum map Sx is just S times the standard momentum map, let me say the K contact momentum map, and it's the momentum map associated with the extended Lie group action, which doesn't move the S coordinate in R cross. And we have that J phi is a K contact momentum map associated with a K contact Lie group action, and then the J phi tilde is a K symplectic momentum map associated with a K symplectic Lie group action, phi tilde. Okay, and we can also relate the tangent spaces to the J phi 2 minus 1 R cross mu on K contact setting and in K contact and K symplectic setting. So it is the tangent space at Sx to J phi tilde minus 1 R cross mu, is given by the d over ds direct sum of Tx J phi 2 minus 1 of R cross K, K mu. So now we know how to perform the modified Marsden-Weinstein reduction for K symplectic manifolds. So we want to translate the conditions from this K symplectic Marsden-Weinstein modified Marsden-Weinstein theorem into the K contact setting, and indeed they translate if and only if these conditions. This condition holds in a K contact setting if these conditions hold in K symplectic setting. And again, they just they ensure that the tangent space, the reduced manifold that is given by the J phi 2 minus 1 R cross K mu divided by this K mu. So in principle, these conditions imply that J iota mu eta bold X intersected with, so the characteristic distribution is given by X is given by the tangent space to K mu of X. These two conditions guarantee that this holds. Okay, and then we can retrieve the K contact structure from the initial K contact manifold, and this theorem guarantees that this quotient is a K contact manifold. Okay. And I don't know if I have time to show you some simple example, because I don't know where I.
Yeah,
in principle,
yes, go
bit?
ahead, because we started a little bit late. So yeah, please.
Okay. So consider M as R5 times R5, and we have local coordinates S1, X1, X2, X3, X4 here, and here we have S2, Y1, Y2, Y3, and Y4. The K-contact structure is given by ds1 minus x2 dx1 minus x4 dx3 plus ds2 minus y2 dy1 minus y4 dy3. So you can see that indeed each of R5 is a contact manifold. So we define the K-contact manifold from the pullbacks of these forms. Indeed, I mean it's easy to check that indeed it gives a K-contact structure on M. So now consider the fundamental vector fields of the following form, that this is d over ds2, x2 xi2m is d dx x3, yeah, and third one is d over dy1 plus d over dy3. Of course, I mean, we have that CIM bolded eta is equal 0. So these vector fields leaves the K-contact structure invariant. So now we define the K-contact momentum map as the contraction of these fundamental vector fields with K-contact, in this case, two contact, the two contact form. Okay, so J phi eta, let me maybe simply denote this as P, is the contraction of first psi1 with eta1. This is eta1 and this is eta2. Xi1m with eta1, which is 0. Then we get that xi2 with eta1 is minus x4, and xi3 with eta1 is 0, plus xi1 with eta2 is 1, xi2 with xi2 is 0, and here we have minus y2 plus y4. And this is in G star 2. Okay, so now we fix mu, bolded mu as 1, 0, minus 1, E2, which means that J phi 2 minus 1 bolded eta of this fixed mu is given by R cross 2 mu is given by x4 equals 0 and y2 plus y4 equal 1. So now you can compute that G phi, the tangent space R cross 2 mu is given by, I mean, ds1, dx1, d over dx2, dx3. Yeah, without x4, and we have d over ds2, d over dy1, d over dy3, and d over dy2 minus d over dy4. Yeah. So now, of course, one has to check that these technical conditions are satisfied by indeed they are. It's just a boring calculation. But it also, actually, in general, you can show that if you deal with the product of contact manifolds, I mean, your contact structure is a product of contact manifolds, these conditions are always satisfied. So indeed, they are satisfied. So now we have to find the Lie algebra K mu. So you can see that this K mu is generated by xi2 and xi1. It's it's 1. So it's plus xi3, which basically means that xi2 eta equals, m equals 0 for x in j phi to minus 1 of r cross 2 mu, and xi1m plus xi3m of eta x equals 0. So K mu is generated by xi2 and xi1 plus xi3. And actually, you can easily see that this indeed holds for such fixed mu. Okay. So now by simple changing coordinates it's maybe a little weird, but somehow natural, but simply calculations. It's 1 plus y3 minus 2s2, z2 is y2 plus y4, z3 is y1 minus y3, and z4 is y2 minus y4. Okay, so now the level, the j2 minus 1 of r cross mu is given by x4 equal 0 and z2 equals 1. Okay, then the tangent space K mu of x is generated by d over dx3 and d over d alpha. So it follows that j phi to minus 1 r cross 2 mu divided by K mu x is a K contact vector space. Yeah, okay, I write it. It's okay. Maybe I will note it. It is, and it gives that j phi. Maybe I will write immediately. That's sorry. J phi to minus 1. You can compute it to bolded mu. K mu is a K contact manifold with this K contact form reduced, given by ds1 minus x2 dx1. Yeah, so we just remove this part from this eta1. And eta2 is a little bit complicated in the sense of calculations, but we get that this is d beta minus 1/2 z4 dz3 d2. Okay, and here we have coordinates s1, x2, sorry, x1, x2, and beta z3, z4. And the reduced Reb vector fields. The first one is d over ds1, and the second one is equal d over d beta. So this is the simple example that illustrates the K-contact Marsden-Weinstein reduction. So thank you for your attention, and here's some literature that we use during our work. Thank you very much.
Thank you very much, Bartosz, for your talk. Are there any questions or comments? No? Okay, I have a question. Actually, I don't remember if we've discussed this before, but in case we haven't, I say it here. You know that there's a new framework to study, let's say, field theories with dissipation, which was the main goal of developing all these things, which is the multi-contact formulation, which somehow combines the ideas from contact mechanics with multisymplectic field theories. And this was first introduced by Luca Vitagliano, I think it was in 2015, but in a very general case, let's say, with people from, well, with Manuel de Leon and with Narciso, who is connected here, and other people, we developed a particular instance of that, which allowed us to work with field theories with dissipation in a multisymplectic way, let's say. And I wonder if this could be extended. Maybe it would be interesting to take a look. I don't know if you have thought about it.
No, actually, we haven't discussed it, but it's
Okay.
totally worth checking, I think.
Yeah, then I told Javi maybe at some point, but yeah,
I mean, I didn't know. So,
okay.
but yeah, thank you.
So any more questions or comments? No? Okay, so anyhow, thank you all for attending, and thank you, Bartosz, for your talk.
Thank you very
In
much.
fact, the talk we have next week is by Leili Mamadova from University of Edinburgh, who will talk about moment maps in multisymplectic geometry. So we will continue with these momentum maps, reductions, and these things. So thank you all for attending, and see you next week. Goodbye.
Bye. Goodbye.